Hi everyone, I'm Talha Ocakçı from javatlon.com. In this video, we will talk about singleton pattern. Most of us think we know the implementation of singleton pattern, but most of us miss some points of usage of singleton pattern in multi-threaded environments. Let's introduce the basics of this pattern shortly to be in the same page with the beginners. Why do we use singleton pattern? Sometimes we use really huge objects like factory classes that are used for creating other objects. Since they are highly memory consuming objects, we want to use just one instance of these objects throughout the application. In this case, we just limit the creation of this object. When I say creation in Java language, constructors must come into your mind. For limiting the creation of this object, we simply limit the usages of constructors. So we hide the constructors from the external world. So we change the access modifier of the constructor to private. When we hide the constructors, there will be no way to create an instance of this class with new keyword. That's why we define a static method to create the instance of this class. Because you know that the static methods are in independent contexts from any instances of this class, and they exist already before any constructed object of this class. Okay, we will see the details soon. For now, just know that we are doing some really cool things to have only one instance of this class, whatever is done by the external world. That's it. When I say only one instance, you should get that this object can be used for some centralized process, because no other instance of this class may interfere to the process. You may think an example such as a single entrance door that is checking the identities and redirecting the clients to the correct desks, okay? That's it. We use singleton objects for preventing high memory consumption caused by huge objects, and we use it for centralizing some process by preventing the multiple instances of this class. Now let's check how to create a singleton object in the simplest form. First, we define a static instance of itself inside the class and initialize it as null. We create the static instance because we want an instance of this class independent of the creation of an instance of this class. We just want to store them inside the static context. So we create a static instance and initialize it as null. After that, as I said before, we are creating a private constructor just to prevent the usage of the new keyword for this class. The third item is we define a getInstance static method. Call the constructor inside this method if the inner instance is null. We define the getInstance method as static because we again want this method to be independent from the creation of any instance of this class. Okay, now let's see the implementation in Eclipse. First, I've created my class called as mySingleton. I'm creating a private static instance of my class, mySingleton inner instance. Let's name it, and it equals to null because I will null check for the creation of this instance. After that, I'm hiding the constructor, the default constructor. Okay, after that I'll create my getInstance method, which is a static method, public static mySingleton say getInstance with no args. Okay, inside it I'm checking if the inner instance is null or not. If it's null, I will construct the object. After that, I'll return inner instance. So if it's not null, I'll return the same instance for each call to the getInstance method. Otherwise, if it's the first execution of the method, the inner instance will be null, and I'll instantiate the inner instance with new keyword and return this instance. This is okay for the single-threaded environments, but this implementation will not be enough in multi-threaded environments. Now let's check why this implementation is not enough in multi-threaded environments. In this implementation, the problem is clear. We have a race condition here because getInstance method is not synchronized, so there is no prevention to block the threads step into these methods synchronously. So when thread 1 steps into the method getInstance, thread 2 may step into the getInstance method too. So both of the threads, thread 1 and thread 2, may initialize the inner instance by stepping into this null check. So thread 1 will create an instance of my singleton. After that, thread 2 will modify this instance. So we need to put synchronized keyword somewhere here. So I have marked the getInstance method as synchronized. Synchronized keyword guarantees that if an object is locked for modification, no other threads may access to this object and wait till the modified thread is done with this object. If a method is marked as synchronized, as in our case, then all the objects in this context are locked for modification. Here we synchronized the method, so only one thread may step into this method. So when thread 1 steps into this method, thread 2 is blocked here. This looks good, but this has an awful drawback. It slows down getInstance call 100 times. Because each thread that is trying to invoke getInstance method will wait for the previous one to complete and step out from this method. So this must be prevented. We only should synchronize the first creation block. So I'm moving the synchronized block inside the lazy initialization block now. I moved the synchronized keyword from the method signature to the lazy initialization block. It seems like we resolved the problem, but we created another problem. Because both threads may step into this lazy initialization block because there is no synchronized block, so both of them is just before the synchronized block, and let's say the thread 1 steps into the synchronized block, so the thread 2 is waiting for the lock which is on the mySingleton class definition. Okay, here thread 1 will initialize the inner instance, but after that the thread 2 will move on execution. So thread 2 will reinitialize the inner instance because the synchronized method only prevents the asynchronous process of multiple threads, but this keyword will not prevent thread 2 to step into this block. So here we need to check the inner instance against null again. We will have two null check. One of them is just outside of the synchronized block and the other one is inside the synchronized block. So let's check this version. In this implementation we have two null checks. Both threads may step into this block and they will wait for each other in this synchronized block. Let's say the first incoming thread is thread 1. It will initialize the inner instance here, and the second thread will move on to this null check, and since inner instance is not null from now on, thread 2 will just return the inner instance. So we have resolved the synchronization problem. Or do we? We have another advanced problem here. Now let's inspect this problem. This problem is caused of the details of memory management of Java. Object creation with new keyword has several non-atomic hidden operations, so it is not a simple single operation. It has multiple detailed operations that are hidden from us. While creating an object with new keyword, Java first allocates a memory for the object and write the related address to the stack space. After that, initializes the object, and after that flush the values to common memory. This common memory means that every CPU process or thread has its own memory. You know that if a thread modifies an object while these four operations are going on, the modification is not visible to the other threads. You should know the ACID properties of transactions. So this is something like the isolation property of these transactions, database transactions. While the modifications are not flushed into the common memory, other threads cannot see the new value of the object. Only thing they can do is that this memory address is not null because this has been allocated by this thread, but the value is not null. So other threads may try to access this object before all the object is populated, like here. Here we have the 300 Spartans, and if the whole Spartan is not initialized, he cannot be used properly. So this is a defect. So we may convert these 4 steps into an atomic operation. One thread must see the totally initialized object, or it must see a null value. There should be no other choice. We use volatile keywords for doing this. Okay, after these explanations, I have put volatile keywords to my static inner instance. So when this instance is tried to be modified, whole the process will be an atomic process. So multiple threads will not be able to interfere with each other while the object is not totally initialized. So we have a thread-safe singleton implementation now.